So there are two ways to make a buffer. There's the direct addition method, which we see here. In this case, we are going to take a solution of a weak acid or base, and we are going to add that conjugate directly to the solution. So we're not doing a chemical reaction. We're literally just adding that conjugate to our existing weak acid or base. The other thing that I could do is that I could react this with a strong acid or base. Say if I have a solution of acetic acid, I could react it with sodium hydroxide. And in that case, I will create that conjugate base in situ in the beaker. So two different ways of doing this: direct addition versus a chemical reaction. So let's look at these problems. This one here is a direct addition problem because I see that I am starting out with 500 milliliters of 0.1 molar HCN, which is a weak acid. I can tell because I've been given its Ka, and I'm going to add the solid sodium cyanide. So one of the most important things about the buffer is the pH, and the pH, of course, is determined by the concentration of H+. And one of the things we really need to do is recognize that when we are given pH, we have an easy way to calculate the H+ ion molarity, because that is such a common thing. Think about the lab equipment we have. We have pH probes. We have pH indicators. We have pH paper. We get pH out of our data a lot. So we need to know that there's an easy way to do that. And it just has to do with the fact that the inverse of a logarithm is the exponent. So if I want to get the concentration of H+ in this solution, then I need to remember that the inverse of a log is an exponent. I take 10 to the negative pH. The pH that I want for my buffer is 9.10. So if I type that into my calculator, 10 to the minus 9.10, that gives me the molarity of H+. It's 7.9 times 10 to the minus 10, and since that's in brackets, I can assume that that is molarity. So then the next most important thing about a buffer, aside from its actual pH, is the ratio of acid and base. Because as long as the ratio of the acid and base stays the same, then my pH will remain the same. So you can use whatever method you want to find that ratio. In this case, since it is specifically asking me for the ratio and specifically asking me for acid over base, I'm going to use that very lovely buffer equation that's on the top of the page. H+ is equal to Ka acid over base. So we can see there is the acid-base ratio. This is what we're trying to solve for. So we need to figure out what this ratio is that gives me the pH of 9.10, which is good. I needed H+. So if I do H+ divided by the Ka, you see that I get the acid over base ratio by itself. H+, well, we just calculated that in the last part. Ka was given in the problem. So this is going to give me the ratio here. I divide that out. I get that my ratio is 1.28. So now I'm actually going to take this exact same equation and the information that I have in my problem, and I'm going to use it to find the molarity of the base solution that I need because I have solid sodium cyanide. So I'm going to take this ratio, which is 1.28, and remember that it is equal to the ratio of the acid over the base. But read the problem. I know the molarity of my acid. It's right there in the problem. So that's 1.28 equals 0.10 over the molarity I don't know, the molarity of the base. So that's just a matter of solving for x. We're going to end up dividing 0.10 by 1.28, which means x is going to be 0.0781 big M. That's the molarity of the base solution, the base, of course, being Cn-. So I need the mass of solid because when I have a solid, I measure it out on a balance, so I get it in grams. But I have no way to get from molarity to grams. There is no conversion between molarity and grams. There's a conversion between moles and grams. So let's use the information in our problem to get ourselves into some moles. I notice here I want to make 500 milliliters of solution, or 0.5 liters if I want to be working in moles. So if I take that 0.5 liters and multiply it by the molarity I now know I need, 0.0781, remembering that big M is moles over liters, you can see now I have some moles. I have 0.0391 moles of sodium cyanide because that's how I get Cn minus ions. And at that point, I am assuming that you can add up the molar mass of sodium cyanide. You can see here the moles cancel the moles, and I get about 1.9 grams of sodium cyanide. So I need to go to the back with my container of sodium cyanide salt. I need to measure it out on a balance in a weigh boat and measure out that 1.9 grams. And then I walk over to my 500 mils of solution and I dump in that 1.9 grams. And I stir it up so that it dissolves. And then I have a buffer because I have both hydrocyanic acid and its conjugate base, cyanide ions. So now I can look at part E. Part E is doing a chemical reaction. I am adding a strong acid to this solution. So a strong acid should react with the base in the solution, and the base, of course, is the cyanide ion. So it's darn handy that I just calculated the moles of cyanide ions because stoichiometry needs moles. Stoichiometry does not care whether those moles are strong or weak. We just need to react moles. So if I am putting in HCl, it is reacting with the base species. HCl 100% dissociates, so the sodium ion and the chloride ion from sodium cyanide and hydrochloric acid would just be spectator ions. So I'll drop them out of my net ionic equation. I now know I have 0.391 moles of this. And to run out of buffering capacity, I need to use it all up. So I would subtract all 3.91 moles and end up here at 0. This is a one-to-one reaction, so my stoichiometry is exactly the same. So if I have 0.0391 here, I have 0.0391 here. And in order for that to actually work, I need to add at least 0.0391 moles. If I add any more than that, I have exceeded the buffer capacity. Of course, this would have started out certainly not as being 0. It would have started out as 0.05 moles from the 500 milliliters times 0.1, and I would react that over here. I would be making more base, so this would get bigger, but I don't super care about that. So, kind of wasting my time. I know that I need 0.0391 moles of HCl. And when I have moles and I need a volume, that is a matter of taking the moles and dividing by the molarity, because that is moles over liters, so my moles would end up canceling out. And you'll notice I'm actually going to end up with a number that I've seen quite recently, because up here I multiplied by 0.5 and down here I am dividing by 0.5. So if I am putting in my liters here, it would be 0.781 liters of HCl. That would give me the number of moles that would exceed my buffer capacity. So when I am doing something by direct addition, I am not doing a chemical reaction. I am adding that conjugate. The conjugate is not a strong acid or strong base. The conjugate of a weak acid is still a weak base. The conjugate of a weak base is still a weak acid. It's just the weaker the acid, the stronger the conjugate base. That's why we don't do weak titrations. So the second one of these problems is doing it the other way, which is where I am generating the base in situ by doing a chemical reaction. It says I want to turn this solution into a buffer. So what I have right now is a solution of HF. In order to make a buffer, I need to put the conjugate base in there. So what is the conjugate base of HF? The conjugate would of course be F minus. So we need to react some of this HF and make it into the conjugate base, F minus. That's why we are adding sodium hydroxide, because the hydroxide ion will react and take the H off of HF to make H2O. Don't really care that much about the H2O because we're not going to appreciably change the molarity of that. But we need to do the stoic, we need to deal with any dilutions if we need to, and we need to deal with any equilibrium problems if we need to. So first things first, we have to do the stoic, and stoic needs moles. If we have a volume, which we do, 250 milliliters, and a molarity, which we do, 1.50 big M, we can get a number of moles, or in this case, millimoles. We'd get 37.5 millimoles. Now that is HF, because this was 250 mils of 0.15 molar HF, hydrofluoric acid. So we're starting with 37.5 millimoles here. And we know that, when we do these things, we generally assume that these start with 0 and they are negligible. So we need to turn some of this HF into F minus, so we have to get rid of some of it. So in the end, we'll have that 37.5 minus some of it that will have turned into F minus, so that we can actually get a buffer solution. Since you can see that these reactions are all 1-to-1, you can see that this would also have to be minus X. And in order to subtract X, we need X to start with. So you notice here, if we solve for X, we're going to get a lot of numbers in this table. So just to be clear, if I am looking at the acid, I am looking at HF. And now I know that when we're done with this reaction, we'll have 37.5 minus X. And if I want to look at the base, I am looking at F minus. And on the F minus, I will have X. So we have a way to look for the acid. We have a way to look for the base. But if we're talking about a buffer, we need a ratio, because the whole point of a buffer is that ratio between acid and base. So we're going to have to do that now. In order to do that, we are going to need an H plus ion concentration, because that's what's in our buffer formula. So if I take 10 to the minus pH, remember, that gives me the H plus molarity. We know the molarity of the buffer we want. It's stated right there in the problem. So we'll take 10 to the minus 3.25, and that's going to give us our hydrogen ion molarity. 5.6 times 10 to the minus 4 molar. We need that ratio, which means we can go right back to our same buffer equation. H plus is equal to Ka, acid over base, and we're going to solve it to get that acid-base ratio, which means we're going to take the H plus, divide it by Ka, and and that's going to give me the ratio of acid to base that I need for this particular pH. We know the H+, we just did it up above here. We know Ka, it's given in the problem. So we can get this easy. This is 0.778. That is the ratio of acid to base. Well, now it says substitute for acid and base. Because remember, back here, we figured out an expression for the acid and the base. So if we can substitute in, we know that 0.778 is equal to the acid part, which is 37.5 minus x, over the base part, which is just x. And now we can solve for x. Of course, we would need to multiply both sides by x to get x out of the denominator. That would give us 0.778x equals 37.5 minus x. Then we would want to collect the x's on both sides, so that's plus 1x on both sides. That'll cancel that out. So I get 1.778x is equal to 37.5. So if I go ahead and divide, so I get the x by itself, then I get that x is equal to it's equal to 21.1 millimoles. So if I have x, and I have that it's 21.1 millimoles, I have that this is 21.1 millimoles, I have that this is 37.5 minus 21.1 millimoles. But most importantly, I have that this number is 21.1, which means this number is 21.1, which means this number right here is 21.1. So that's the amount of OH minus that I need to put in. I need to figure out how to get 21.1 millimoles. Now, if it was a solid, I'd just convert it to grams and go mass it, but it's not. In the problem, it says that I have a 0.1 molar NaOH solution. So I need to figure out, how do I get 21.1 millimoles of NaOH when I have a 0.1 molar solution? Well, 21.1 would be equal to 0.1 moles over milliliters times some volume of milliliters, which is why you end up dividing by the molarity. That cancels that out, and I get that this is 211 milliliters of NaOH. The reason that this works is because I can take that 21.1 and put it in right here. This is now 21.1, and this is now 21.1. So this is now 21.1, and this is 16.4. There is both acid and conjugate base in solution. So that's why this works, because now I have a buffer. I have both the acid and its conjugate base. So notice that there's a lot of very similar steps in here. I use the pH to get my H+. I use the Ka, because that's Ka in my formula. I use the Ka to get the ratio of the acid to base. And then if I'm doing a direct addition problem, like I did up here at the top, I'm going to know the molarity of one of these things, so I can put it right into my equation and solve for x, just like I did here. If I am using direct addition, then I am going to have to take that ratio, and remember that I am taking out some of my existing species and converting it in to the conjugate. So I'm going to have to solve for x. And then it's just a matter of, what do I have? In this case, I had a solution, so I needed to find the milliliters. In the top case, I had a solid, so I just needed to figure out how many grams of that solid I needed to put on my balance. So hopefully that will help, and hopefully those good practice problems will help, and we'll get some points back and have a good start.